Okay, yeah. Thanks, Venkat, and thanks to the organizers for this workshop. I really wanted to be there, but I guess you'll be exposed to another Zoom talk. So yeah, I'll be talking about this problem of testing homomorphisms and try to give a general recipe to cook up such tests between arbitrary pair of finite groups. And this is an upcoming joint work with Sawyer at the University of Iowa. Okay, so what's the setup? There's two finite groups, G and H, which just means a set which has a multiplication operation and an inverse. And I can look at the space of all functions between these groups, which is just a set theoretic function. It doesn't care about the group structure. But clearly, there's a natural subclass of functions that does care about the group structure. So homomorphism is just a map that respects the multiplication. So for every pair xy, f of x times f of y is f of xy. Right? So this is a very natural class of functions. In the coding theory language, if you think of the space of functions as your points, this homomorphism is a code. It's a subset of the points. So it's called the homomorphism code. Right? And it's a very natural class of functions. And the key issue here is that this is a very rigid object, right? So it says that for all points, x and y, you must have an exact equality, right? And a very recurring idea in TCS is to have robust notions, right? It could be because you have some sort of noise and there could be some corruption. So even if you start with the homomorphism, you don't have one, or algorithmically, it's not feasible to check such conditions, right? You can check only some sort of relaxed notions of these. So there are two very natural ways to make this definition a bit more robust. So the first is to drop the for all condition and then say that this homomorphism property holds for a constant fraction of pairs. So this equality is not true for all pairs, but for some constant fraction. And this is the perspective we're going to take and look at more general versions of this. So this is the kind of notion that pops up in this testing literature. And another thing that you could do is you could drop the equality and retain the for all. So that's discussed in what's known as stability or uniform stability, where for every point, you don't have an exact equality, but then you have approximate equality. And this thing can be formalized if you use some sort of metric on the target group H. Okay. And what's the high level picture? The goal is that you have this approximate notion of what it means to be a homomorphism. And then from that, you would like to deduce some true structure, right? So this is kind of like an inverse result that you want. So for this talk, I'll focus. This work is focused on the testing regime, and I'll define these things in more concreteness later. But let's start with this kind of a definition. So this was the genesis of all of this is in the seminal work of Blum, Lumiere, and Rubenfeld, who defined this as an algorithmic test, right? So this delta is this fraction of points on which the function does behave like a homomorphism. And this you can think of as an algorithmic test where you're sampling points x and y at random, and then you're checking if this equation holds. Okay, so with any function f, this is just a number. Right? And this is a very elegant definition. It holds for any groups G and H. Right? It doesn't care about the groups. And the question that we would like to answer is, okay, if I give you this number delta, what can you tell me about f? Right? So for instance, if delta is 1, that's equivalent to the function being a homomorphism, like a genuine homomorphism. But let's say delta is 0.7 or 0.1 or 0.01. Right? So what can you imply about f? What kind of structural properties can you deduce? And the kind of property we want is to say that it agrees with a true homomorphism at a significant fraction. So what we want to say is that there exists a true homomorphism phi such that the fraction of points they agree with. So this is 1 minus the normalized Hamming distance. That is bounded below by some function of delta. And ideally, we'd like this function of delta to not include the size of the group and H. Right? So it should just be a function of delta and not the sizes of G and H. Okay, so this is the kind of conclusion we wish to draw just from this number delta. Okay, so what do we know about this such a result? So there are two very distinct regimes that people study this in. the high soundness and the low soundness regime. So in the high soundness regime, we have that this delta is pretty large. So the function, behaves like homomorphisms on a very large fraction of points, right? Close to 1. And here we have a very good idea. So in particular, if I pick any pair of finite groups, we have such an inverse result. Okay, so this was proved by Dinur, Coppersmith, Lupi, and Rubenfeld, and then later people have generalized this also to settings beyond finite groups. Okay, and the key idea in these works is usually that when you have such high soundness, so when you have such high agreement, then there is usually a unique homomorphism that agrees with your function, if at all there is. And this unique homomorphism can be reconstructed using a majority decoding procedure, if you've heard that term. And therefore, it's kind of a constructive way of showing that there is a homomorphism. And that's why this regime is also called the unique decoding regime. Okay. And there is a bunch of literature on de-randomized tests and so on, but it's a fairly complete picture that we have there. On the other hand, in the low soundness regime, I don't place any lower bound on delta. Right. So I would like to have some structural result about f without assuming that delta is large. Right. So 1 over h is like a natural trivial bound because a random function obeys that. So anything slightly better than random, you would like to obtain some results. And here we have very few results. So the classical case naturally was the case of Z2 to the n to Z2, where if this test passing probability, this delta, you get an agreement of delta. So that's kind of optimal, and that's how we want our parameters to be. And this is generalized to ZP, but here already we see a kind of loss. So Harsha Wigderson generalized this to the case of ZP, but now you have an agreement of 1 plus delta over P. So remember, I truly want this function to not depend on my group sizes, but here this is a very small agreement when P is large, right? So this is one result, and then the other result that we have is the setting of the Freeman-Ruzha conjecture. So this is the case when you have maps from Z2 to the n to Z2 to the m. Think of n and m being very large. So Sarnowski first gave a result for which the agreement was like inverse exponential, and the Freeman-Ruzha, the polynomial Freeman-Ruzha conjecture, is equivalent to saying that this agreement can be made polynomial. And so Sanders made it quasi-poly, and then the recent breakthrough work on PFR, which resolves the PFR, gives that this agreement is a poly. And I think the best polynomial known is delta to the 9. Okay, so this is, to the best of my knowledge, the exhaustive set of results giving such an inverse result. Right? So you can clearly see there's a huge difference between the high soundness case that we know and the low soundness regime. Okay, and so clearly there are a few examples that we know. Moreover, like I said, for ZP to the n to ZP, we have a weak result. So the maximum agreement we have, it's at most 2 over P. Right, but that's quite weak. Like even if your delta is approaching 1, then you must have that the function is very close to homomorphism. But this is kind of vanishing as P increases. And one could say that maybe it's a weakness of analysis, but actually there are reasons why we don't have this test for general groups, right? So Coppersmith gave a very simple counterexample, and the counterexample is just says that for any k, think of k, any integer, you can cook up a function for which delta is pretty large. It's 7 over 9. But this function does not agree with any homomorphism at more than 3 points. So this agreement is variable. Think of k, large enough. But your delta does not really witness this. Your delta is kind of fooled into believing it's quite like a homomorphism. So what this says is that this kind of a definition, this kind of a BLR-based definition of an approximate homomorphism cannot capture this in the low soundness setting for even cyclic groups. So we can't hope this for general groups for this to be true. Okay. So what is needed is a new test. And Kiwi is very interesting work, defined a new test for the case of ZP to the n to ZP. Right. So he just modified BLR kind of a bit. And he actually also proves it for some sort of families of linear codes that are subcodes of this. But with that, he could fix the first issue. But we have this open question for a very general setup. How do we design tests for some other groups? So before we proceed, I'm going to define what I mean by homomorphism test more formally. So the setting is that there's a function for which you have query access, right? You can ask it questions about points, and then it replies with f of x. So k-query test naturally can ask it the function value at k points, and it obtains f of x1 through f of xk. And after I receive this, the algorithm has to make a decision as to whether it is a homomorphism or it's not. Okay. And the conditions that this algorithm must satisfy are what's called perfect completeness. So if I gave you a genuine homomorphism f, so if f was truly a homomorphism, then I must always output yes, no matter what queries I make. On the other hand, if my function does output yes for a function with probability delta, so the probability here is over your random choices of queries, right? So if you're outputting yes with a probability delta, then this function better be correlated with a true homomorphism in the sense that it agrees with it in this Hamming sense. So there is a homomorphism phi, it's just that it agrees with f on at least an s of delta many points. Right? So that's the soundness. Right? So the goal now is to design such k-query tests. Yeah, please feel free to stop me if you have any questions. So the key question that we wish to address in this is, okay, you come and give me a pair of groups G and H. How do I come up with a test? Right. So we've seen that BLR cannot really do it beyond at least a few cases. And how would I come up with a test? The elegance of BLR is that it's so general that it works. Like it's well defined, but it doesn't work. So we want a general definition, as general as we can get, and to also then analyze them. So another kind of bottleneck in this low soundness regime is that earlier analysis kind of depend on Fourier-based proofs. And yeah, for an arbitrary H, it's not probably the useful tool because you cannot really embed H into complexes or the scalars. Okay, so you need like more general ways to analyze these things beyond Fourier analysis, what's called the physical space proofs. Okay. And another question is that if I give you more queries, like if I ask you to give you the freedom of making more queries, you should be able to give me better guarantees, right? So can we get some sort of a smooth trade-off between this? So the BLR, as you've seen, is a 3-query test. It samples a pair x and y uniformly at random, and then it queries the function at x, y, and x times y. Right? So it's a 3-query test. So how do I get a general k-query test, and how does my guarantee improve? And so this is the set of questions that we will at least partially try to answer. Okay. All right. Yeah. Stop me if there are any questions. But let's start with the one case that we've seen BLR be not very good at, which is the case of cyclic groups. So let's imagine you have a function between z mod p square z and z mod p square z, right? So this, I can just represent it as cycle, right? So I've just plotted like some important points. So there's 0, there's 1, and there's all the multiples of p. Now, any true homomorphism, what does it do? Well, it maps 1, so it has the freedom to map 1 to any element. And then correspondingly, every other element is just multiplied by I times the following element, right? So what happens is 1 maps to I, and every element x maps to I times x modulo p square. Okay. But what this forces you is that any multiple of p is always mapped to multiple of p, right? So here, if you see all these purple points, will always be mapped to purple points. So that's how a true homomorphism would behave. Whereas if I picked a random function, then it could send f of p to any point, not necessarily a multiple of p. Okay, it's a very, very simple kind of an observation. So let's say now, if I gave you this guarantee that either the function that you're trying to decide between, either it's a true homomorphism or it's like truly random. By random, I mean that f of x, I just pick it to be one of the p square values uniformly at random. And let's say I fix f of 0 to be 0. Okay. So on one hand, it's completely structured, so it's homomorphism. And on the other hand, it's truly random. And I just wanted to distinguish between that using a single query. So it's kind of a silly toy case. But based on the previous slide, right, it would make sense. It would not make any sense to query f of 1 because f of 1 can be arbitrary. Right. So any homomorphism phi can map 1 to any possible value. So just by looking at f of 1, you have learned nothing about the function. But whereas if you query f of p or any multiple of p, then you might be able to tell it apart. Right? Because if f of p is not multiple of p, then you've identified that your function is not a homomorphism. Right? So all this is to say is that there is a distinction between the elements in your groups. Right? So it's not that all elements of your groups give you the same information about a function being a homomorphism or not. And that is something that the BLR test does not use. Right? It just samples the element uniformly at random from the group without really looking inside the group. And which is why it kind of does not perform very well on the cyclic case. And this toy setup is just to motivate that what one would need is some sort of a custom distribution on G or G to the K on the set of tuples that you are going to pick. It has to use the group in some sense. Right? And then the key question is, okay, how do I come up with this or some sort of arbitrary group G? Is that okay? I guess it's hard to get feedback on a Zoom talk, but okay, so that's the goal. So I wish to come up with some distribution that uses this kind of a property of the group. And the key sort of idea in this thing in our work is to say that we are going to cook up this distribution kind of looking backwards, right? So it's like instead of trying to define a distribution and then analyze the test, I'm going to look at how the test is going to be analyzed and then define the distribution based off of that. Right? So that's a kind of a inverse kind of procedure as to what is usually done. So what is my goal? My goal is to cook up a test such that this equation holds, such that the maximum agreement with the homomorphism is lower bounded by some function of this test passing probability. That's what the soundness means. But now the max is a very hard quantity to work with. So one wants to work with like some sort of smoother approximation of max. And what one can do is instead of using the max, I can always approximate it by like an expectation from some distribution over the homomorphisms. Right? And now I can pick this distribution to be something very natural where phi is. So if I give a weight of this agreement to the k to phi, then and if I compute this expectation, I just get this simple. This is a simple inequality. And this procedure makes sense. Like you want to look at phis, you should give it more weight if they agree more with the function. Right? And just to clarify, this is not an algorithmic procedure. This is just to get the inequality. We're not really going to sample any homomorphisms here. But using this, what we're going to shoot for is try to approximate this kth moments. Right? So we have this sum of the kth powers of this agreement. And we're going to try to write this as some test passing probability. And this is the goal, to define such a test. Okay. Right. So the way we do this is by really using this very simple but like very, very useful map, which is in a certain sense a dual object. So fix any tuple of elements x1 through xk sitting inside G to the K. So these are each xi belongs to the group G. Now I can define a very natural evaluation map going from the space of all homomorphisms to h to the K, where my phi maps to just the tuple of evaluations. So phi of x1 through phi of xk. Right? And more importantly, if G and H are abelian, then this map is also this is also a group homomorphism. So this would have to be modified when the groups are non-abelian, but I'll not discuss that in this talk. But this map is also a homomorphism. So it has nice properties. For example, it's always n to 1. Right? The pre-images have the same size. So either they are 0 or they are just exactly n, which is a very useful property. Okay, and the key lemma, which is once you have these definitions in place, it's not very hard to prove, is that this kth moment you can rewrite in terms of this gamma. So it's an expectation of overall tuples, the indicator whether your function belongs to this image of gamma times the kernel. Okay, so this is some algebraic manipulation. And coming back to our goal, we would like the right hand side to be the test passing probability. Okay, but once you read it in this manner, then and you stare at it, like, the test kind of just pops out. So just looking at this expression, this right hand side is like a sampling procedure. So what it says is that you sample a tuple x1 through xk based on the size of the kernel of gamma x. Right? So here, this is how the group structure is being used. So this gamma map is encoding both the structure of the group G and the space of homomorphisms, because it's a map from Hom GH to G. So it's using the information of both G and H. Right? It's not the uniform distribution. And the test is simply that you check whether your function is in this image of gamma. Okay. And it has perfect completeness, because if F were a true homomorphism, then by definition, it lies in the image of gamma, because gamma is just mapping homomorphism to all their evaluations. But for true homomorphisms, it definitely is in this set of evaluations. Right? So image of gamma X is just how all homomorphisms would look like. Right? And if you work this out for the cyclic case, you start to get the toy case that I mentioned. So this kernel depends on the order of elements. So it would give more weight to multiples of P. Okay. And what this would give you is that this moment, this kth moment, you can write it as a constant depending on the group G and H, which has nothing to do with the function F, times this test passing probability. And now all you have to do is to compute these constants gamma k for your favorite groups G, H. So the general recipe as follows: you have this defined test. You try to bound this for the smallest possible k you can. Right? Sometimes for smaller k's, this quantity can be large, but for larger k's, you can get better results. You just plug it back into this kind of an equation, and you get some result. Okay. For various reasons, this might not work, but you can make a couple of fixes. So one reason it might not work is the first inequality is weak. Right? Remember that the first inequality is an approximation. So this happens even for the linearity testing kind of setting. But what you can work with is like some sort of thresholded moment. So you only consider these agreement if it's large enough. So that way you avoid very small noisy homomorphisms. And then you can also slightly tweak the distribution. Like you can explicitly forbid looking at certain elements. So again, in the cyclic case, I don't want to look at f of 1. Right? It does not give me any information. So I would just rather only sample things that are multiples of P. Okay. But this gives you a fairly general starting point. And from there, depending on your group structure, you can tweak this a bit and try to get a low soundness test out of it. Okay. So now I just mentioned the results. Are there any questions on what this framework is, what's happening?
Tushant, you have about 7 minutes or so.
Okay, perfect. All right. So then I'll just mention the results. So so we've implemented this kind of procedure for a family of groups. So firstly, we can handle this case of GQ to the n to GQ for prime and prime power speed. So remember, for the BLR case, you had some suboptimal, like you have 1 plus delta by P kind of a guarantee, but now you can get here like the optimal, close to optimal delta up to some exponentially small error, and this recovers the result of KV. The KV is modification. So this kind of recovers that result. More importantly, for any pair of cyclic groups, you get a 3-query test with soundness proportional to delta. And this is like small contents is at least half. And this is the Coppersmith's counterexample. So this overcomes Coppersmith's counterexample. And now you can generalize the cyclic case to some more families. You can take the target group to be any abelian group with bounded P rank. So bounded P rank just means that when you decompose the abelian group into sum of cyclic groups, then you can have at most T many cyclic groups that are a power of P, right? So for that bounded rank case, the number of queries increases with the rank, but you get a similar guarantee. And then you can extend it to cyclic groups that are not necessarily prime of arbitrary order. And in the unbounded rank case, you can get it when the base group is just ZQ and not, when the target group is ZQ to the n. So it cannot contain arbitrary powers of P. But more interestingly, we can also get an example for the non-abelian group. So here, the group is the dihedral group, so which is the group of all symmetries of a p-sided polygon. So it's rotations plus the reflection, right? So it's a non-abelian group, and this is first example of a case of non-abelian group in which you have this testing result. So like for example, in this kind of a case, it would be very hard to try to use full analysis or even some kind of representation theory to get this. But our proof gives a very physical space proof. So even for Z2 to the n to Z2, the BLR proof is very Fourier theoretic, and this gives a physical proof of that. How they're quite related. Yeah. So here, now if you give me more queries, so here K, I pick anything at least one, right? So now you see an improvement in the soundness in the exponent. So I'll just hide the constants and you get delta to the 1 over K, right? So if you let me make more than the minimum number of queries, then I get this improvement. So as K increases, I get better and better guarantees. Okay. And this, and an interesting corollary of this kind of an approach is you get list decoding bounds, right? So for any function f, the list L epsilon is just the set of homomorphisms which have agreement at least epsilon, right? And we would like to bound the size of this list, bound the number of homomorphisms. So just recall that the key thing we are doing is that we are writing this kth moment and we are bounding that, right? So since probability is at most 1, you have an upper bound of this thing in terms of this gamma constant depending on your groups. So what you directly obtain is a list size bound of 1 over epsilon to the k if your gamma k is bounded by some constant, which you can prove for at least some families of groups. So and these are better than known bounds, at least in some regimes. So if your groups are cyclic, let's say prime order, then we get list size of 2 over epsilon square. And I think the best result in this scenario is by Dinur, Grigorescu, Koprasti, and Sudan, which gives a list size bound of 1 over epsilon to the 105. Right. So their work is more general. They can handle any pair of abelian groups, and there are generalizations to solvable groups. But that uses a very combinatorial inductive kind of an approach. But when you instantiate that for the cyclic group case, you get a much worse bound. So this improves that, and you actually just get it for kind of free with this approach. And another important thing is that you can use algebraic homomorphisms, right? So if the homomorphisms between your group are controlled by homomorphisms over some other group A comma B, and you've already computed gamma AB, you can kind of reuse the analysis, right? So it's not an algorithmic reduction, but it's a reduction in the analysis. So using this, you can generalize the results to slightly more general settings. So for example, if you have a map between any group to FP, right, the map factors through its abelianization, right? And then you after a couple of isomorphisms, you just reduce to the case of ZP to the n to ZP or FP to the m to FP. So you can also handle this by this approach. And the interesting case, I guess, in the last two are that's called the character testing problem, right? So where you have an arbitrary group G, and then you want to think of the target being either complexes or in this FQ case, the invertible elements of FQ. So these are the one-dimensional representations, right? And in the second case, you have these are all linear maps between n by n. So GL and FQ is all n by n invertible maps, right? And these are all these are all invertible matrices over FQ, and these are all matrices M, not necessarily invertible, but the extra property I need you to satisfy apart from being linear, is that they are like this cyclic invariant. So think of it as a trace function. So these are what I call the algebra homomorphisms, and yeah, they just are controlled by the homomorphisms of the group ZQ to ZQ. Right? So this can just you don't have to do much. You can just reuse this computation. So it's a neat thing you get out of it. So I guess I'm almost out of time. So I'll quickly summarize. Yeah, the last part is kind of quick, but it's just to give you a flavor of the flexibility of the approach. So yeah, what we've seen is kind of like a general recipe, right? For any pair of group G and H, this procedure of sampling a tuple based on the size of this kernel of the dual map is fairly general, but at the same time, it uses the group structure, right? So BLR is also general, but it's very black box. It doesn't use any structure of the groups G and H, but this kind of approach uses that, and therefore can work out in cases where BLR does not. And the test is a very natural test when you just rewrite the moment expression, right? You don't have to it also sort of resolves, at least to me, the mystery behind Kiwi's test, why Kiwi's test works. Right? It's not ad hoc. And what you have to do to actually instantiate this is to sit down and do a bunch of group theory computations. Okay. And there are, of course, very natural problems is to investigate more and more groups with this kind of an approach. Maybe you have to do some more tweaks. Maybe you have to modify this distribution in more interesting ways. But we feel that we can handle many more situations here. And one thing I've not spoken about is the randomness used to do this sampling. And there's this usual question of de-randomizing such tests. And because these are higher query tests, like the K query for larger K, HDX is a very natural kind of candidate to de-randomize thing. So yeah, this is at least to me a very interesting question. And can we go beyond even group homomorphisms? Can we study more structured objects via a similar approach or some modification of this? So yeah, that's all I have. So I'll let there be time for questions.
Yeah. Thanks a lot, Tushant. Any questions?
Hey, Tushant, can you hear me?
Yes.
Okay. Nice talk. But is there a hope of, inspired by my PCPs and CK's talk before you, is there a hope of a two-function version? So f of x times f of y is equal to f prime of x times y, where f prime can have some relation to f, but it's not the same.
I've never thought of such a variation. But is f prime, so there are variations of this studied when, so let's say you have function over the symmetric group, and then you get a guarantee on, so even if you had something on or rather let's say this, right? You have a function from G to the d by d unitaries, right? Then instead of giving me a guarantee of such a function, you give me, you embed this into a larger matrix of d primes by d prime. So there are those variations known, but yeah, no, this I've not thought about.
Okay. No, it's a vague question, but yeah. So.
Yeah.
Hi, Tushant. Can you hear me?
Prahladh, yes.
So, nice talk. This question more on the type of test. So one thing about the BLR test on F2N or the Reed-Muller test, for instance, if you draw the underlying test graph, that is the graph between the tests on one end and the code word bits on the other end, these cases, these are actually very nice graphs. They are part of these larger complexes or some such thing. Are the tests that you discuss for various other groups also the corresponding test graphs also very nice graphs, or what's the graphs that you get?
Okay, no, very interesting. I mean, of course, so here because of this weighting, right, it would be a very weighted graph. Yeah, I don't know if I've seen this graph before, but yeah, maybe these have been studied in some sort of a manner. But I mean, I kind of also mentioned this some sort of a culling, right? Like, I mean, in BLR, you actually truly sample every possible element. Oh, can you see my thing, or did I just?
Yeah.
So here we actually also sample from a subset of the. So we forbid all tuples. So this D is like also like a strict subset of G to the K. So it might not even be a graph on the full space of points. You see, like it'll be like a subgraph of that, even if it's been in some natural way. So I doubt that is the case, but yeah, it's a nice thing to think about. Yeah, but yeah, it'll have a wacky weighting, even if it is.
So I had a question. So you mentioned this soundness trade-off. There are these results, for example, for linearity testing, saying that you can recycle queries more efficiently, so you can get some better trade-off. If you instantiate your thing with a large K, would you beat those results or match those results?
Yeah, I doubt because okay, yeah, I've probably not spoken about this randomness computation, right? Because to sample from this distribution might take more than what it would take for just like the uniform because of this weighting. So I'm not sure that it would beat it, but I guess that's the hope if you do these queries in a I mean, classically you do an expand a graph, or if you recycle in that kind of a manner, then there is hope to beat those. But otherwise, I like as presented here, I don't think it would be better than that.
Okay, great. Any other questions? Okay, if not, thanks again, Tushant, for the great talk.
Thank you.